Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in the previous lecture we were discussing cluster analysis, and specifically we talked about the distance matrix that could be used to compute the distance between two clusters. We also did an exercise in R to understand those discussions. Now let us continue our discussion on the same topic today in this lecture. So, few important points about deciding which distance metric the distance metric to use to compute distance between two clusters. So, there are certain points which could be helpful in making this particular decision. So, one is first one is certainly the domain knowledge. So, it is the domain knowledge, the problems at hand, the data set, the problem that we are trying to analyze, that for which we are trying to build a model and analyze. So, that particular domain, the problem domain, will actually in a way can guide us in terms of what distance metric would be more suitable for computing distances between clusters. So, then the second thing is the nature of cluster. Nature of cluster will also drive this computation. For example, if the nature of cluster is like chain or sausage then probably the minimum distance metric could be a good choice. Because this particular distance metric, the way the distances are the way distances are measured, it tries to identify the closest observations from two clusters, and in a way it is linking up those chains. So, this particular metric is like friend of friends kind of scenario, and because of this the kind of cluster shapes for which this metric could be suitable are like chain or sausage like clusters. So, the same thing we can understand here. For example, so if this is one cluster and we have the another cluster here, and we have certain observations in each of these clusters. So, let us call this cluster as A and this cluster as B. If we look at the minimum distance metric, probably we will find out the pair of observations which are closest to each other, and these are the two observations, each one belonging to each of these clusters which would be identified, and then this distance is going to be taken as the distance between these two clusters. So, in this fashion, if we look at these clusters, if there are more than two clusters, then you would see a chain kind of thing forming. So, because of this, the the clusters which are chain like, which are more of a chain like clusters, for those or sausage like clusters, for those situations this minimum distance metric could be a better choice. Examples: land or marine mines. So, typically if we look at the minings, how they are how they are laid down, or how they are whether it is about laying the minings or it is about finding out the mines, in whether in the land or marine, typically they are around a particular border area. So, the mines are typically laid down along that area. So, therefore, if we are looking to identify the cluster of mines, then probably the minimum distance metric would be a better choice, because they would be along something, and because of that the connecting them would be easier for us, or understanding this particular this kind of observations would be better for us if we use the minimum distance metric, because the nature of those clusters, because of their formation along something, right, because of their formation along something, they would form like chain like or sausage like clusters. Similarly, one more point, similarly we will talk about other distance metrics, but before we move ahead, one more point about minimum distance metric. So, minimum distance metric works well even if some observations are not close to one another within a cluster. So, this is another scenario where this particular metric could be useful. However, one important point that it is expected that new additions in a particular cluster should be close to some observation in the cluster. So, to understand this particular point, let us see here that the observations, for example, if we look at this particular cluster A, there could be a distance observation here, and here we have this observation. Since though these observations are distant from each other, still they are part of the same cluster. So, this is the point that was being made here. So, even if some observations are not close to one another, still they can be part of the same thing, and minimum distance metric could make that happen, because distance between clusters are being being computed in this fashion. So, a distance observation belonging to this cluster A can still be there. However, as the point also notes here, that the observation, that distance observation should be close to some other observation. So, you can see here this particular observation is close to some other observation, so that it can become part of this cluster A. However, if we look at its distance from this particular observation, then we can see here that it is a distance observation, but still part of cluster A, and the minimum distance metric is allowing this to happen in a a suitable manner. There are some other cluster types for which different metrics would be useful. For example, spherical clusters. So, spherical clusters, the maximum and average distance matrix could be good choices. For example, customer segmentation using several variables. So, we look at the maximum and average distance matrix. So, the way distance between two clusters is computed, either the farthest pair of observations are involved, or all possible pair of observations are involved. So, is essentially the way this computation happen, this is going to be more suitable for spherical clusters. Customer segmentation, because typically this is done using a number of variables. When we use a number of variables, then essentially it is along many dimension, and distance computation is along many dimension, and the kind of values that we get because of this, the observations are going to form a cluster in a spherical fashion. So, because of this, if we are encountering such clusters, then probably these are the maximum and average distance metrics are the one that could be used. And if we talk about some other situations where the nature of cluster, the shape of cluster is not well known or not understood, even in those situations these metrics, maximum and average distance matrix, can be used, because this is the natural tendency. Because if we are going to do distance computation using a number of variables, so because of this the natural tendency of clusters is to be spherical, and because of this maximum and average distance matrix could be found to be more suitable. So, these were some of the points which could be helpful in terms of deciding which metric is going to be useful for what kind of for different kind of situations. So, this discussion brings us to our next part. So, that is as we talked about in previous lecture, that we would be covering hierarchical agglomerative clustering and k-means clustering, one technique from each of those two types, hierarchical methods and non-hierarchical methods. So, within hierarchical method we are covering this one, hierarchical agglomerative clustering. Within non-hierarchical methods we would be talking about k-means clustering. So, let us start with our discussion on hierarchical agglomerative clustering. So, the main idea behind the agglomerative clustering we have already talked about in previous lecture. So, let us understand the algorithm and its steps. So, in this particular algorithm, the way clustering happens, so typically we start with the n clusters. So, each observation is going to be seen as one cluster. So, each observation is going to be equivalent of one cluster. So, we will start with, if there are n number of observations, so each observation would be considered as a cluster having a single observation. So, we will start with, essentially we will start with n clusters. Now, Out of these n clusters, as you can see from the step number 2, two closest observations are merged to form one cluster. So, out of these n clusters that we start with, so these all n clusters are nothing but n observations. So, we try to find out the observations which are closest to each other and then join them or merge them. So, this merger leads to creation of one cluster having two observations. So, in this fashion we move forward. So, if we look at the third step in this algorithm, it says that in the next steps two clusters with the smallest distance are merged. So, now after the step number 2, what we have is one cluster having two observations and the remaining n minus 2 clusters. So, now within these total, so now total we have n minus 1 cluster and one of them having one of them having 2 observation and the then we have the n minus 2 other clusters. Now, within all these clusters n minus 2 clusters, we again try to find out the 2 clusters which are closest and then merge them. So, either so what is going to happen now is either single observations are added to existing clusters. So, for example, we have one cluster with two observations. So, either some other observation can also be added to this cluster or our single observation clusters, two of them might be merged together and one cluster could be formed. So, either single observations are added to existing clusters or two existing clusters are combined. So, these are the two scenarios. So, in this fashion we keep on moving. So, we keep on finding either the two closest observations or two closest clusters or one observation being close to some other cluster. So, in this fashion we move ahead and essentially what will happen is, as we talked about in previous lecture in the agglomerative clustering, essentially we will end up with just one cluster having all the observations. So, let us go back to RStudio and let us go through a few exercises to understand these concepts. So, before we move ahead, in the previous exercise in R, we were able to cover the we were able to compute distances using single linkage, complete linkage and average linkage, but we also talked about another metric that is centroid distance to compute the distances between clusters. So, let us also go through this exercise first and then we will move further. So, if we have two centroids, if we have two clusters A and B and we want to compute the centroids for these two. So, what we will do first we will use this particular information, the DF1, where we had the normalized scores. So, if we are interested in first 5 serials, so we can we run this code and we will get this information. So, for first 5 serials and normalize scores on rating and price we can see here. So, why we need this information? Because we need to compute the centroids. So, for computation of centroid, we need values for all the observations that are part of a particular cluster. So, if we look at the next code, so here we see that what we have is the mean values here. Mean values are being computed using the observations 1 and 2. So, because first 2 rows, high protein cereal and health card breakfast cereal, they are part of the cluster A, as we talked about in the previous lecture. So, these two observations are to be used to compute the average value for these two dimensions, rating and price, these two variables, right. So, you can see mean is being taken for these two values 1 to 2, that means essentially just 2 values. We look at the for the next centroid, we can see here is that for this particular centroid, the second centroid, we are considering 3 observations. We are 3 cereals, Special K multigrain and honey, then Choco chocolate and Choco's duet. So, 3 to 5. So, these 3 rows are being used to compute the average value. So for these two variables, rating and price, we will get the mean values, and these values will this particular computation will actually give us the centroid for the two clusters. So let us run this code. Now you can see the row number 1 is giving us the centroid for cluster A, and the row number 2 is giving us the centroid for cluster B. So we want to use we want to compute the distance between two clusters using the centroid distance method. Then essentially what we need is we need to compute the distance between these 2 points. So for this we can use the distance function again, and just like we had computed the distance matrix for these 5 serials. So here again we have 2 points and we need to compute the distance between these 2. So we can use the dist function and we will get this value. So let us run this code. Now you can see the value has been computed. So this is the distance between these 2 centroids that we have just computed, and essentially this is going to be taken as the distance between 2 clusters. So this is the centroid distance method for us if we want to use this particular metric to compute the distance between 2 clusters. Now let us start our discussion of hierarchical agglomerative clustering, that this algorithm that we have discussed just now. So again for understanding this particular algorithm further, again let us consider these two variables once again, customer, rating and price, and we will consider first 5 serials only to understand this discussion. So again before we move ahead, we need to have the distances between distance value between different serials. So for this we are going to use this particular matrix which we have already computed. So this is using Euclidean distance metric on normalized scales. So this particular matrix we had computed before. We have seen this before in the previous lecture as well. So let us run this, and in this matrix, as we saw in the previous lecture, we can see each of these serials and the distance between each of these serials with the remaining serials. So these distance values are available with us. Now once these distance values are available with us, remember the first step in the hierarchical agglomerative clustering. So let us go back to our slide. So you can see start with n clusters, and then the second step is 2 closest observations are merged to form one cluster. So we need to identify 2 closest observations. So that is going to be the important task here. So to find out the 2 closest observation, we can run this code. So what we are doing is we are taking the minimum value of this distance matrix dm1, and within this, because the matrix is symmetrical, we are just taking the lower triangular and we will get the value. So let us run this code. So this is the value 0.039625557. This is the lowest distance between two observations. So let us find out which observations have this value. So we go back. So we will see that where so this is the value, we can see this was the value. So this value is between these 2 cereals, Choco chocolate and Special K multigrain and honey. So these 2 are the cereals which are closest. So as we understood from the algorithm, 2 closest observations are merged to form one cluster. So as indicated in the algorithm step, now we will plan to merge these 2 observations, Choco chocolate and Special K multigrain. So these 2 observations will be merged to form one clusters, and then we will have the remaining observations as clusters, individual clusters with single item, right. So essentially what will we left with, so one particular cluster having 2 observations and 3 other clusters with having single observation. So essentially now in terms of distance values, distance values for clusters, we will have to compute this 4x4 matrix. So you can see here. So let us initialize this 4x4 matrix. So you can see here initialization has been done, and now we are going to, because the names of these serials are they are quite long, so we'll do some abbreviation here. And you can see here a high protein cereal now is going to be used as HPC, and the health card breakfast cereal is going to be used as HBC, and similarly other cereals, they have been abbreviated, and these abbreviated names are going to be used now. So this 4 matrix that we have just now created will change the row names and column names, so that we are able to understand which particular cereals we are talking about. So let us change the row names. So first we are changing the row names for DM1, our original 5 cross 5 matrix, and then we will do this the same for the 4 cross 4 matrix. So DM1, let us run this code. Now you can see in the DM1 where we had the 5 serials, the original matrix, distance matrix, and we had identified this is the these two are the closest serial, CC and SKMH. These were identified to be the closest. Now we will need the 4 cross 4 matrix, which we have already initialized. So let us change the row names and column names for this particular matrix as well. And you can see here, now you can see the third cluster, we have renamed this one as SKMH-CC. So this is because these two observations have been clubbed or merged to form one cluster. You can see here the cluster has been these two observations have been merged into one cluster, and the cluster has been renamed as SKMH-CC. So now what we need to do is we need to find the distances between these clusters. So some of these distances can be directly taken from the 5 cross 5 matrix. For other distances, now we need to see out of which two observations. So we in the cluster SKMH-CC, out of there are two observations, one is SKMH, the another one is CC. So which observation is closest to the other clusters observation, and then that is to be that minimum value, because we are using here minimum distance matrix formula. So therefore that particular value is going to be used as the distance between those clusters. So let us have a relook at this DM1. So this is the DM1 5 cross 5 matrix having 5 serials and the distances between them. Now if we look at our 4 cross 4 matrix, first distance that we need to compute is, look at the matrix, first distance HBC between this cluster HBC and HPC. So we need to compute this value. So this value can be directly taken from DM1, as you can see here. So let us run this. Then this is important, the next one. So next value is between we go back, next value is between this cluster of two observations SKMH-CC and HPC. So this is the value that we need to compute now. So if you look at this, because we are using minimum distance matrix, I am using the min function, and there are two possible values, right, DM1 from SKMH to HPC, and then CC to HPC. So out of these two values, the value which is minimum is going to be taken as the distance, right. So as discussed, let us run this. Now similarly for other distances, we can run this code and we will get these values. So it is only 3 distance computations where this cluster with 2 observations, that is SKMH-CC, this cluster with 2 observations, and the remaining 3 clusters. So those 2 distances are the one where this minimum distance matrix is going to be used. Now to complete this particular matrix, let us run this part of the code and we can print this now. So you can see in this 4 cross 4 matrix we have all the values now up to 2 decimal places, you can see here. And let us look at the values with more decimal points. So this is the matrix. Now you can see. Now if as the next step, if we go back to the algorithm here, again in the next steps 2 clusters with the smallest distance are merged. So again our task is quite similar. Within this 4 cross 4 matrix we need to identify which 2 clusters are closest and then merge them together. So first we need to find out the value. So distance values we already have. Now we need to just find out the minimum value here. So let's run this code and we'll get the value. So this is the value which is minimum 0.6356365. We try to find this value in this matrix. This is the value. So it is actually the distance between CD, that is the cluster with single observation CD, and our cluster with 2 observation SKMSCC, which is the closest, right. So this CD cluster with single observation CD is going to be merged with cluster with 2 observations SKMH-CC. So this is going to be the next merger, and it will lead us to a 3×3 distance matrix. So in this fashion we can keep on following the steps of algorithm, and you would see that we'll have the full processing of these clusters, and finally we'll end up with one cluster having all the observations. So this was the exercise that would have given us the understanding of about how this algorithm is going to work. So let's move ahead. So let's talk about the difference distance matrix and how they influence the HAC algorithm. So if we are using minimum distance matrix or single linkage matrix in HAC, so what are the important points? So let's discuss them. So what happens when we use this minimum distance matrix is there is this tendency to cluster even the distant observations at an early stage due to swelling with a chain of intermediate observations in the same clusters. So as we talked about, because the observations even the distance observation can be part of the same cluster because of the minimum distance matrix that we are using there, because intermediate points with are going to be there, and they will allow this to happen. So what we will essentially lead to elongated sources like shaped clusters. So as we talked about that if the nature of clusters that we have they are chain like or sausage like, then minimum distance matrix is one suitable matrix. Similarly, if we are using minimum distance matrix in our clustering method, then also we can end up with these elongated sources like shaped clusters. So it goes both ways. So for this kind of cluster with this kind of shapes, the minimum distance matrix would be suitable, and similarly if we are using the minimum distance matrix, then we might end up with having clusters with these kind of shapes. Similarly, for maximum distance matrix, so there is a tendency to cluster the observations lying in a narrow range from each other at the early stages because of the farthest distance, but within a farthest distance because of the distance that we are using is between the farthest observations from each of those clusters. So because of this, but this particular distance is going to be a narrow range because it is the closest clusters which are going to be merged, right. So all the clusters and the distance between those clusters, even though we would be computing them using maximum distance and will get the distance values based on the observation which are farthest, but when we apply the algorithm, it is the clusters which are closest, they are going to be merged. So therefore we will get a narrow range observations which are lying in a narrow range, they are probably going to be merged together, and therefore the kind of shape that we get is typically spherical. So if we are going to use maximum distance or complete linkage matrix in HAC, then typically we might end up with spherical shaped clusters. Now if we are using HAC, if we are HAC in our implementation of HAC, if we are using a single or complete linkage, then it is important one point that is mentioned here, that it is the order of inter record distances that is the whole process depends on this particular order, and not the actual values. As you can see here, even though the distance computation are using minimum distance or maximum distance, right, but if we look at how those clusters are joined, it is the clusters which are closest. So whether you have measured your distance using minimum or maximum distance metric, the clusters which are closest, they are going to be identified and joined. So therefore it is the order of those inter record distances which are going to matter and not the actual values. So even if certain linear transformation or some other kind of transformation happens and distance values change a bit, it might not matter because the order might still remain same. Therefore we might end up with the same clusters. So it is important to understand that it is the order, because we need to identify two closest clusters, and if the order remains same irrespective of the metric that we are using, minimum or maximum, then probably we will end up with same kind of results. So with this we will stop our discussion on cluster analysis, and in the next class we will discuss the another important method, agglomerative clustering method, that is Wart's method. So we will discuss this one in the next lecture. Thank you.